Okay, dear students, let us now discuss the next topic, which is moment of inertia. In this, we will be discussing first of all about the moment of area. Okay, the moment of inertia is basically the cumulative product of area and square of its distance from an axis. Okay, and this is given by this equation. Ix is equal to integration of y square into dA. What is dA over here? dA is nothing but the area representing the area of a small element, which is having the dimensions of dx and dy, as you are seeing here in this figure 5.1. And y is the distance from the x-axis in this case, because we are having this ix on the left hand side, which is representing the area moment of inertia about the x-axis. Okay, and y is the distance of the small element from the x-axis. And if we integrate this over the domain, that means over the whole of the area, that you are seeing an arbitrary area over here, so we'll find the total moment of inertia about this x-axis. And similarly, the moment of inertia of a section about the y-axis is given by integration of x squared, where x is the distance of the small element, area element from the y-axis, into dA. dA is the again the dx into dy, which is nothing but the area of the small element. Okay, so this is the general equation that we will be using to find out the moment of inertia of the entities or sections that we will discuss later in this video. Okay, now if we want to find out the total moment of inertia, the cumulative moment of inertia, the cumulative product of area and square of its distance from a point is known as a polar moment of inertia. Okay, so that derivation is also given over here, which is nothing but given by this equation 5.4. Okay, now table 5.1 is very important because it provides you commonly used sections. Because later on in your later courses on strength of materials and other courses, this moment of inertia of these sections will be used frequently. So it is good idea to remember at least some of the very commonly used sections and what are the moment of inertia. Okay, for rectangle, this is for the axis which is passing through its center, it is BD cube divided by 12, where B is the breadth and D is the depth. Okay, and for triangle, it is BH cube by 36. Okay, and for circle, it is pi D raised to power 4 divided by 64. And these are this is for semicircle, which is typically half of this in the y direction, and in the x direction also it is given. But if you don't want to remember this for semicircle, that is perfectly fine, no problem. Okay, now I will be discussing another theorem which is applicable to find out the moment of inertia in many cases. This is the theorem of parallel axis. So straight away coming on to the figure 5.7 to explain this, we can say that if you have an arbitrary area which is shown over here, and you find out the moment of inertia by using the formula that we discussed before, and you have the moment of inertia of this figure in your hand, and this is passing through. Moment of inertia is basically the first moment of inertia that we find out is basically about the axis which is passing through its center of gravity. Okay, but if you want to find out moment of inertia of this figure about another axis which is parallel to the axis which is passing through the CG. For example, the axis which is passing through the CG is x-axis in this case, and you are interested to find out the moment of inertia of this figure about Lm instead. Okay, so you can simply find out this by taking the using this equation, which is Ixx, which means the moment of inertia about the axis xx, plus area, total area, into h square. H is the distance between these two axes. So this is the parallel axis theorem. Okay, and similarly there is another theorem, which is theorem of perpendicular axis. So in this theorem of perpendicular axis, you have again an arbitrary area. Okay, and the derivation again, you can easily go through. It is again the integration over the domain, over the area, and you can find out the formula that I am going to discuss. So suppose this is the area, arbitrary area, and you have a small element which is here, and you find out the distance from y-axis and distance from x-axis given over here. And after you integrate by finding the moment of inertia for this figure, okay, you will ultimately get this equation, okay, which is IOZ is equal to IOX plus IOY. So what does this mean? This is if IOX and IOY be the moments of inertia of a lamina about mutually perpendicular axes OX and OY in the plane of lamina, and IOZ be the moment of inertia of the lamina about an axis OZ normal to the lamina. So this equation typically helps us to find out the moment of inertia of the lamina about an axis which is perpendicular to its plane. Okay, so by because we know this moment of inertia about the x-axis and y-axis, or which is passing through its CG, we can easily find out the moment of inertia about the z-axis. Okay, so this is about the moment of inertia. So we can have some problems, discussion of some problems, solved examples to further understand this moment of inertia problems.